Our first speaker is Sara Sulway, who's our Product Strategy Manager for Rock Knowledge, based in Perth. And Sara's going to talk about why location matters, why spatial integrity drives geological confidence. So I'd like to invite Sara to come up and give her talk. Thank you.
Okay. The phrase location, location, location. It's very commonly used to describe property value. The better location, the higher the price. In our world, in the world of mining and exploration, that same phrase can be used to describe something just as valuable, and that's confidence. So there are an array of tools and activities that a geologist will undertake to gather information about that rock, about its mineralogy, petrophysical properties, texture, structure, grade. The vast majority of that information comes from drill holes. The more information we collect, the better the geological interpretation, and the more confident we are in that, or at least that's the theory. The confidence that we place in those geological interpretations and subsequent resource estimations is really important, because that confidence is what resource companies base their decisions on, whether to proceed with the project or to put it on hold. Similarly, investors use that confidence to decide on which companies they're going to invest with. So the value of the data collected and how it's interpreted has a direct impact on the cost of these decisions. Before we get to talking about data quality, grade, mineralogy, structure, and the level of confidence we have in that, there's one question that we need to ask ourselves. Do we know where it came from? Where is its location? So spatial integrity is the founding principle on which all subsequent steps in the process of geological interpretation are built upon. If you don't know where that rock sample came from, its depth and its orientation, all that other information that you're collecting around the grade, the structure, the mineralogy is completely and utterly useless. In exploration and mining, decisions around resource classification, around mine design, and around investing hinges on the accuracy of that spatial data. And even small errors can propagate into large consequences. Now, spatial integrity isn't owned by one discipline. It's a shared responsibility. Drillers control where that hole is located and how it is drilled and how that data is collected. Whereas the job of a geologist is to interpret what the rocks are telling us. Now, both of those things have to be correct in order to have a high confidence in your resource estimation. If the hole isn't where we think it is, the geology can't be trusted, no matter how experienced the geologist or how sophisticated the model. And equally, a perfectly drilled hole will lose its value if that spatial referencing data is not collected and preserved and passed through into the interpretation. In short, whilst geologists build that confidence, the drillers create it. So geological confidence emerges from an interplay of multiple sources and multiple data sets. All of them fundamentally rely on spatial referencing. Now, we know that geology doesn't appear as straight lines and nice sharp angles. So does it really matter? Do a couple of degrees here or there really matter in the whole scheme of things? The short answer is yes. The reason that spatial errors are so damaging is that they don't appear as dramatic failures. They are small errors that go unnoticed a lot of the time, but they propagate and they grow as you progress through each of the processes that lead up to your geological interpretation and your estimation. So that couple of degrees out in the orientation mark that it's made at the rig, as the core moves through the process to the markup stage, that couple of degrees, if it's not picked up, it can be escalated and compounded. That passes on to your orientation line, which is used to take your structural measurements. Every single step and every single small mistake is compounded, and the uncertainty footprint by the time you get to your estimation and modeling and estimation process grows. So small errors or small spatial errors right at the start of that process can turn into big downstream consequences. The ultimate impact of those is incorrect structural interpretations, geological contacts not being where you think they should be, and ultimately re-drilling, re-logging, and unreliable decisions. So where is confidence won and lost? Well, I can tell you where it's not created, and that's in the modelling process. Confidence is created when the survey is run, well, the rig is aligned, the survey is run, when the core is orientated, and the data is checked. It happens at the rig. Okay? It's the backbone of the entire interpretation process. Once bad spatial data is collected, no amount of software can fix it. Fun fact, geological databases don't deteriorate over time. They're quite unique. You think of other types of databases in, say, telecommunications companies. You have names, you have addresses, you have contact numbers, emails, the plans they're on, the names and contact details of the family members that are on that plan. Every single piece of, or every single one of those pieces of information can change over time. Geological databases don't. They are what they are. You can certainly go back and extract more information out of them at a later date, but once bad data is collected, it's there to stay. So let's look at how confidence is created. Why are missed targets and increased drilling costs an industry reality today? Even when the tools that are deployed to collect spatial data at the rig are using accurate and well-calibrated sensors. So if we think about downhole surveying, most of the time, I think most people will think of the output of that as being a measurement. So you have an X, Y, Z coordinate, you have an azimuth, and you have a dip. That gives you the whole trace, a line in space. But the real value of downhole survey comes from the QA/QC data that runs alongside it. It's that data that wraps around each of those data points and tells you whether that line is trustworthy and why. That's where the value is. That QA/QC data prevents surprises. It helps us to determine the types of errors or problems that may exist. They can fall into different categories. They can be operational errors, they can be tool or data quality errors, and they can be errors that are created as part of the environment and the conditions in which they're being run. So if you see a quality flag, for instance, triggered very early on, this can point to a setup or alignment problems. Now, these are the kind of operational errors that are completely and utterly fixable at the rig, on the spot, if they're picked up. Then you've got things like closed loop error checks. So this is the misclose. This is essentially a trust score for that particular drill run. If your downhole surveys going down the hole don't match your uphole surveys within a particular tolerance, then that is a quantified signal that something has drifted or moved or behaved in an unpredictable manner through the run. A very large misclose result can suggest a drift in the gyro, in the calibration issues, or mechanical instability. Variance and standard deviation are not just random stats. They also give you a lot of information around about the reliability of that measurement. It tells you whether the tool is stable. High standard deviations can indicate that you've got poor centralization or excessive vibration or drag. All of this degrades the confidence. So the punchline here is that the QA/QC for downhole surveys turns a single measurement into a defensible, audible data set. It tells you not only where the hole is going, it also tells you whether or not you can trust it. So let's talk about core orientation. Whilst the downhole survey information gives you, tells us where the hole went, the core orientation process tells us how it was orientated in the ground before it was extracted. Now, these two data sets are inseparable. If the hole path is uncertain and the core orientation is perfect, it doesn't work. Conversely, if you have got an inaccurate, a perfect hole and an inaccurate core orientation, it gives you a false confidence. Now, core orientation is generally considered notoriously unreliable. Not that surprising, really, when you consider that even though the sensors in these downhole tools are highly accurate and precise, when they come back up to the surface and they're put out on the racks, you give a marker to a human being who draws a little mark on the face of that core. Now, it doesn't matter how careful that human is, they're not robots. Trying to repeat and put a consistently good mark on the core every single run is difficult. So what we've done here at IMDEX is create the IMDEX core orientation tool. And I'm going to give this a shameless plug. It was one of the first projects that I worked on when I joined IMDEX. And I'm incredibly proud of it because the first time it is giving both the geologists and the driller that QA/QC information wrapped around that core orientation mark that helps them to determine how reliable that mark is. So at the rig, the driller knows at the end of the run what went wrong. We have a client here in Canada who was informed, like a lot of drillers are, that no mark is better than a bad mark. So unless you are very confident that nothing went wrong during that drill run, do not mark the core. After using IMDEX for several months and recording the progress, they reported a 10% increase in the number of on the amount of reliable core orientation marks put on that core. Now that's 10% more marks, that's 10% more reliable structural data in your database. That information also allows geologists, when they're doing the markup and their structural measurements, to determine which ORI line is more reliable when you core locks together, but your ORI lines don't match. It can tell them whether or not that drill string was stable. Was the tube still rotating? Was there excessive vibrations when that core orientation reading was taken? Was the hole approaching vertical? So the accelerometer was having difficulty to actually determine where the bottom of hole was or bottom of core was. All this information can give the geologist data and allow them to make informed decisions about which line is more reliable and which may need adjustment. It also allows them to assign confidence ratings to each drill run with a lot more clarity. That confidence rating, of course, can then be transitioned across into your structural measurements and then into your your geological interpretation. So again, core orientation by itself doesn't create confidence. Trustworthy, auditable orientation data does. So now looks like about how geological confidence is built. So while it's created at the rig, it's built during the modelling process. Now, rather than thinking about this process as a workflow, an iterative workflow or linear thing, think of it as a dependency chain. You have your downhole survey, which gives you your spatial sort of referencing and spatial context and framework. You have your core orientation, which informs your structural information. And then you've got your rock knowledge. So this is all about your mineralogy, your grade, your structural readings. Geological confidence is only as strong as the weakest link in that chain. If any one of those links breaks or is cracked, then confidence drops, decision-making slows down, and costs go up. QA/QC turns problems into explanations, not surprises. So what does this actually mean in practice? Well, for the drillers, their actions at the rig directly affect the confidence in that geological interpretation. The care they take at the rig can save re-drilling, prevents reinterpretation, and protects trust in the data. Whereas for the geologists, having spatial data that they can trust results in fewer assumptions, stronger interpretations, and more defensible decisions. Geologists need understanding, not blind trust. So to sum up, geological confidence doesn't start at the model. It starts at the rig. QA/QC is your friend. Right? It is there to help and to prevent surprises. And it ensures that decisions are made on data that can be trusted. And lastly, everyone contributes. Drillers, offsiders, geologists, field technicians, even people like me who work for technology companies and who are involved in developing the tools and the software that deliver this information to allow more trustworthy, more confident interpretations. Everybody contributes, just at different points in that dependency chain. Thanks for listening.
Thanks, Sarah. It's just reinforces all these messages about confidence and continuity in managing your data and your data streams. Thank you.